Hello everyone! Today we will learn about automated software testing in a very fun coding exercise. We will take a GUI application and we will use it to understand what to test and how to test it. So by the end of this video, you will finally understand why testing helps us write better software, because it is not always clear. Now, I highly encourage you to warm up your fingers and code along with me, because these type of practices is what really separates beginners from professionals. So without any further ado, let's roll. And we will begin with some starter files, which you can download from my GitHub, and the link is as usual in the description. Now inside those files, you will find an assets folder with 2 images, as well as a my app Python file, which is basically the Kivy application that we are about to test. Now, ideally, when we design tests for our software, we usually do it before the software exists. It's a bit challenging, but this is considered to be the best practice. Today, however, we will do the second best practice, where we already have a piece of software that we're quite happy with, but we're still not exactly confident that it's as accurate and as secure as it gets. So let's fix it. So first things first, let's run this app. And on my end, I'm using Anaconda. If you're not sure what it is, please check out this tutorial of mine. It will make you an expert. Now let's quickly enlarge the font. We'll slightly rearrange the screen. And let's go ahead and create a brand new working environment with conda create -n, and we will call this environment test39 because we are installing Python 3.9 in it. We will confirm with Y, and we will activate this environment with conda activate test39. Now, once we are inside the environment, we will go ahead and install Kivy with pip install Kivy. And that's the only requirement we have. Now, once everything is installed, we will navigate back to our project folder. We will copy the path and we will paste it back in our terminal following a cd command, as in change directory. Then once we are in the exact same directory as my app, we will type python myapp.py. And beautiful, here's our lovely Kivy application. And right away, we can see that it deals with the Pythagorean or Pythagorean theorem. If I mispronounce it, I apologize. I'm an immigrant. I do have an excuse. But the idea is, if we know the lengths of 2 sides in a right triangle, then this app will help us calculate the third, based on this lovely formula we've all learned in school. So realistically, if leg A has the length of 3 and leg B has the length of 4, then hypotenuse, I hope I say it right again, then hypotenuse C should return 5. So if we press submit, beautiful, we get 5. Now what happens if we specify A as 3 and C as 5? We get B as 4. And since we get a floating point number, I'm assuming we are allowed to specify floating point inputs. And there you go. And perfect. Everything works. We are getting the expected results. So are we done testing yet? No. We haven't even started, because what we've done so far is not what we mean when we say software testing. Manually pressing buttons is only fine if we do it once, but since we test our software on a regular basis, we need to find a way of automating this process. That way, we write our tests once, and then we can repeat them anytime we'd like, especially when we make changes to our software. Now, we usually begin testing with something called static analysis. This is where we review our code without running it. So we are only looking, we are not touching yet. Now, we can of course do it with our own eyes, but since this video is all about automation, we will do it with software. For this, we will install a static analysis library called pylint with pip install pylint. And then pylint will review our code and notify us if any issues are found. So let's type pylint myapp.py. And we will do this super quickly because this is not as important as the rest of this video. This is just a very, very good practice. So let's hit enter. And holy smokes, look at all these issues that pylint found. And this rewarded us with this very embarrassing score of 5 out of 10. Yikes. So let's say that we went over all these issues line by line, we have maximized our score, and we are super happy with the results of our static test. What's next? Well, we move on with something called dynamic analysis, where we are not just looking, but we are also touching. We are executing or running our code in order to test it. And yes, it is the fun part. Now, for this, we will create a brand new file and we will save it in the exact same directory as our app. We will call it test_myapp.py and let's hit enter. Now, the first item on the menu is to import the app we are about to test with import my app, which is basically the name of the file minus the .py extension. Now, in addition, we will also import the unit test library, which will help us with our automated tests. Now, before we start coding, if you're not familiar with concepts such as classes, inheritance, Kivy, or unit testing, don't worry. I have a whole bunch of tutorials that will help you understand each of these. You can find all the links in the description, and in addition, I will pop the relevant tutorials on the screen as I speak or as we code along. So let's begin. Now with unit test, we encapsulate all our tests inside a class, which we will call test my app. And this class inherits all the methods and all the attributes of another class called unittest.testCase, where test case is written with a capital T and a capital C. Awesome. Now, right below, we will define our very first test, and we will call it test_my_first_test, or any other name you'd like. Just please make sure it begins with the keyword of test. Otherwise, it's not gonna work. Now let's quickly turn this function into a method by passing the self parameter into it. And if we're already here, let's add a placeholder, some print statement, and let's just print yo. Now lastly, we will need an additional block of code at the very, very end of our file saying if name equals main, then we will run all our unit tests with unit test.main and an empty set of round brackets. And that's the basic syntax we'll be working with. Now, the general idea behind unit testing is that we want to assert that something is true. So we are making sure that a certain condition is met. If it is, then we pass our test and we can move on to the next one. If it is not, then we make changes to our software and we continue changing it all the way until we are able to pass the test. But what exactly are we testing? Which brings me to my awesome testing checklist that you can find on my GitHub. I will explain and demonstrate most of the checklist items, so please feel free to use the timestamps to skip anything you already know. Now, the first thing we test is the existence of elements. Is it there or is it not? Or alternatively, can I access this element when I need it? So at this point, we don't really care about the content. We only care if our classes, functions, assets, or other software elements are manifesting. So let's see an example. For this, we will rename our test to test_app_exists. And how do we check if something exists? We simply check if it is not none, where none represents the absence of data or simply nothing. For this, we will use a statement called self.assert is not none in camel case. And as you may guess, this statement will receive our app as an argument. But how exactly can we target our app? So let's go back to our myapp.py file and let's navigate below. Let's look for the command that runs our application, which is something that we usually find at the very, very end of the file wrapped in an if name equals main statement. Now, in our case, we run the app with pythagorean.run. So let's quickly copy Pythagorean because we don't want to type it again. And back in our test file, we will create a local variable inside our first test called app, and we will assign it to myapp.pythagorean. Remember, because we are importing my app, we need to specify my app in front of the Pythagorean class. Okay? Now, let's quickly print it right below just because I want to have a quick look. Ooh. And lastly, we'll pass it into our assertion. So there you go. App. Awesome. Now let's save it. Let's quickly run it with Python test_myapp.py. And lovely. We ran one test and we passed it given this lovely OK. We've also printed our app object, which doesn't tell us much, but this is how it looks like. Great. We now know how to test for the existence of classes. We can now move on with some other checklist elements, for example, UI elements, also known as widgets. So all the buttons and all the inputs and all the labels, we want to make sure that users are able to see them and they are able to interact with them. Otherwise, our app is kind of useless, right? So let's take care of that. So let's go ahead and find the widgets in my app. Now, we can clearly see that they are not inside the Pythagorean class because it only contains a single method, which means that our widgets must be inside the other class called user interface. Now, besides the very logical name, we can see inside the docstring that our widgets are expected to be here. And if we scroll down, we can double check that we see the content of our widgets. So great, we found them, but how are we supposed to select them if our app lives inside the Pythagorean class, but our widgets live inside another class? Well, this will require a bit of reverse engineering. So let's scroll down to the very bottom of our app, and starting from the run command, we will trace the execution path of our program all the way until we find our widgets. Okay, you will see what I mean shortly. So first, we run our Pythagorean class, and our Pythagorean class returns a user interface object when the build method is called. So realistically, Pythagorean.build should return the user interface, right? So let's test if it works. Back in our test file, we will create a brand new test called test_GUI exists, where GUI represents graphic user interface. We'll of course pass the self parameter into it, and let's copy the content of our previous test because we don't want to type it again. Now, we are no longer interested in the existence of the entire app. We are only interested in the existence of the interface. That's why we will create a new variable called GUI, and we will assign it to app.build, which is pretty much the results of our reverse engineering, right? So let's go ahead and pass GUI into our print statement. And we will also assert that GUI is not none. Let's save everything. Let's give it a run. And beautiful, we ran two tests. Both of them are okay. And we have printed our user interface object as well as our app. Awesome. But how do we know that this user interface object contains our widgets? For this, we'll need another test. So let's go ahead and copy our GUI exists. We'll slightly modify it. So we will change the name to widgets exist. And before we assert anything, let's make sure that we are able to access these widgets. Now, I'm going to save you some time and I will reveal the command that will do it. It's called GUI.children. Okay, so if we save the file, if we run it, we can verify if our interface contains some children elements. Okay, let's run it. And there you go. GUI.children returns a bunch of buttons, grids, labels, images. So great. Let's go back to our test and fix it, because if we're not asserting anything, we are not testing anything, right? So to make things consistent, we will create a new variable called widgets. We will assign it to GUI.children. There you go. And we can have a few variations to our assertion. So first, let's make sure that widgets exist. But this doesn't help us understand how many widgets we have. Maybe some of them are gone, right? So let's go back to our print statement and let's count how many widgets we are expecting to see. We have 1, 2, 3, 4, 5, right? So let's go ahead and use a different type of assertion. This time we'll do assert equal, and we will pass the length of widgets as well as the integer 5. Cool. Now another variation, just from the top of my head, we can iterate over the widgets with for I in widgets, and then we can assert for each widget that it exists. So let's go ahead and copy this. Assert is not none. Okay, and then instead of asserting whether widgets is not none, we will assert whether I is not none. Okay, so all the roads lead to Rome. We can verify that all of these work at once by running our code. Man, we get an error because I have a typo. Assert equal. I'm sure you noticed it. Let's give it a run. Okay, great. We ran 3 tests and all of them are passing, but we just bundled 3 different assertions in a single test. How do we know that all of them are true rather than just one? Let's quickly change 5 to 4 and let's see what happens if we tamper with our code. There you go. Now we are failing, not because of my typo, but because 5 is not equal to 4. In other words, if one of our assertions fails, it means that the entire test has failed. Now, the last example of existence deals with assets. In our case, 2 images that our app contains. We want to make sure that these files are actually there before we try to load them. And that's exactly what we will do in our next test. Now, let's go ahead and quickly define it. We'll call it test underscore assets exist. And to make it work, we will need to import the OS module, which will help us with all the path variables and some general file system commands. So up at the very top of our code, we will import OS, and then we will use it first to fetch our root directory, our project folder. We'll do it inside the test, okay, using an os.get cwd and an empty set of round brackets command. Now, what CWD stands for is current working directory, okay? In our case, let me demonstrate that. That would be the starter files directory where test underscore myapp.py lives. And since it happens to be the exact directory where myapp.py lives, this is perfect for us, okay? Now let's quickly go ahead and assign this getCWD expression to CWD, a local variable. And then we will use this root directory to figure out the path to our images. What do I mean? We will use an os.path.join command to which we will pass CWD first. Then we will join it with the assets directory where our images live. And for each image at a time, we will specify its name and its extension. So for example, diagram.png in such a way that the commas help us specify the root directory, then the assets directory, and then the image itself. I hope it makes sense. If it doesn't, please let me know in the comments below and I can cover OS in a separate video or just help you in the comments as well. Cool, so let's go ahead and assign this path variable to image 1. And we will do the same for our second image. We'll just copy this line of code. We'll adjust image 1 to image 2 and diagram PNG to logo PNG. Great. Now we have the paths to our images. We only need to check if a file exists in this path, right? For this, we will use another OS command called os.path.is_file. And to this method, we will pass each of our image paths one at a time. And if a path indeed contains a file that is accessible and not corrupt, this entire command will return true. Okay, so isFile can only result in true or false. That's why we will use one of my favorite assertions here, self-assert equal. We will then copy our isFile command. We will paste it as a first argument. And then if everything works as expected, then this argument should return true. If an image is found in this path, then we have passed our test. Okay, that's basically what we're doing here. Okay, we'll do the same for our second image. Okay, let's save everything and let's make sure it worked. Okay, let's rerun our test file once again. And boom, we ran 4 tests and those tests were successful. How do we know for sure? Let's tamper with diagram. Let's say diagram 1, 2, 3. Okay, let's try to pass our test again. Okay, and there you go. We fail because false is not true. Now, just because an element exists, it doesn't mean that it's the right element, and it doesn't mean that it works as expected. So in the next category, we will focus on the content of our elements, where the first checklist item is the data type. So for example, if our function is expected to receive integers only, it should only receive integers. Or alternatively, if our output is expected to be a dictionary, but somehow we receive a string in return, this means that something is wrong and we must fail our test in order to demonstrate it. So for this, let's see an example in code. Back in myapp.py, we will navigate to the Pythagorean method of our user interface, not the Pythagorean class, the Pythagorean method, which you can find on line 129. My apologies about naming them so similarly. I should have thought of it earlier, but let's refer to it as Pythagorean with a lowercase p. Okay? And if we look inside this method, we can see that all the return statements return a dictionary, right? So it doesn't matter which scenario happens. In all cases, we get a dictionary of strings. Cool. So let's test it. So we will go ahead and copy our widgets exists test. We will paste it at the bottom, and we'll then get rid of everything below GUI, because we don't need it. Now let's quickly rename this test to dictionary exists, or whatever name you'd like. And then since Pythagorean is a method of our user interface, if we type GUI.Pythagorean and an empty set of round brackets, this lovely command should always return a dictionary. So let's quickly assign it to output. Okay, now to test if a certain element has a certain data type, we will use an assertion called self.assertIsInstance, where the first argument is the element, in our case output, and the second argument is the data type, in our case dict or dictionary. Now, if we're already here, we might as well verify that it's a dictionary of strings. For this, we will create a for loop for key val in output.items. We will then copy our assertion from above and we will slightly modify it. So let's assert that our key is an str or string. The same way we will assert that our value is a string. So instead of key, we type val. We're pretty much good to go. Let's save everything and let's give it a quick run. And lovely, we ran 5 tests and we passed them. Great success. So let's say we checked all the data types and all of them are correct. But just because something is of the right type, it doesn't mean that it has the right value. So how do we know that our math is correct? Well, we'll probably need to send some input into our app, and then we can determine if this input results in the expected output. Now, I know it sounds a bit complicated, but we've done most of the work here. So for the next test, we will go ahead and copy our widgets exists. Should have been exist. My apologies for the grammar error, but we will just leave it as is. Okay, we can get rid of everything below widgets because we don't need it. And we will modify the name of this test to input AB. And as you may guess, we will send a value into input A. We will also send a value into input B. Sorry guys, my cat just jumped. Again. We'll wait until he sits properly. Nia, can you sit? Give it some time. And if we're already here, we might as well fix my typo from earlier. It's not going to make much difference, but it looks better that way. Now, the first thing we'd like to do is we'd like to select our inputs. Okay, we will do this using a list comprehension where we print the index and value for index and value in enumerate widgets. Okay, we simply want to know which of the items in this list is the item we're looking for. Okay, that's why we're printing its index. So back in our terminal, we will rerun our test file. Okay, and there you go. Here's our list of widgets. The problem is that none of them is the text input we're looking for. So what's going on here? Well, we can see that the item at index 1 is actually a grid layout. And it's significant because our entire user interface is also a grid layout, which means that this element probably contains other widgets inside it. And let's assume that our inputs are over there. Okay, so back in our code, we will go ahead and select, actually before we do so, let's make sure we are printing all the widgets that are nested inside this new grid layout. And we will do this by enumerating widgets in the index of 1.children. That way we can see all the nested elements that we couldn't see earlier. So let's rerun our code. And beautiful, there you go. We get 3 text inputs, along with their labels, of course. But then how do we know which of those inputs is A, which of them is B, and which of them is C? Now, the long way is to print the text of each label, and then the text will reflect on the nature of the text input. To save some time, we will assume that the text input at index 4 is A, and then the text input at index 2 is B. And let's select our inputs accordingly. So when it comes to input A, okay, we'll create a new local variable for that. There you go. Then to select A, we will first go ahead and select this nested grid layout with widgets in the index of 1.children. We will then wrap it in a set of round brackets where we'd like to focus on the child at index 4, if it makes any sense, right? Because all we did is we copied our content from enumerate and we focused on the item at index 4, which we have determined is our text input. Hope it makes sense. If it doesn't, please leave me a comment below. I'll try to help. Okay, we'll do the same for input B. We'll change A to B, and we will change index 4 to index 2. Great. Now we selected our inputs, but now we need to send some text into them, some values. We will do this with a very, very simple command. Input A.text equals a string of 3. We will do the same for input B. We'll target its text attribute, and we will assign it to 4. Okay, so realistically, based on our previous examples, hypotenuse C should have the length of 5, based on these specific inputs. Now, how do we get the output of our Pythagorean method? We already did it before, so let's just copy our output variable from the dictionary exists test. We will paste it right at the bottom of our newest test, and then we can go ahead and assert if the output is equal to 5. Okay, the way to do so, we will add a self.assert equal statement to which we will pass our output, okay, as well as the return statement of C. Okay, how do we know how this return statement looks like? We know for a fact it's a dictionary, right? We might as well wrap it like that. And back inside myapp.py, we will look for the scenario where the user provided a value for A, so it is not equal to an empty string. We have also provided an input to B. It is also not an empty string, while C remains an empty string. And in this case, our return statement looks like that. We have a dictionary with a key of C and a value of whatever this variable returns, right? So back in our test file, we will go ahead and specify the second argument of our assert equal statement as this lovely dictionary we just copied. And then instead of the local variable of C, I guess we are expecting to see the string of 5, right? Because we're dealing with a dictionary of strings. Now, if we save everything, if we rerun our test, we are failing. Holy smoke. So let's see what's going on here. And wow, folks, I think we just found an actual problem in our code that we couldn't find earlier. The actual return dictionary is not a dictionary of strings, but it's a dictionary of floating point numbers. Wow. Okay, well, what happens if we are failing a test? That means that we need to modify our original code, myapp.py, all the way until we pass this test. Okay, now the way to do so is back in myapp.py, we'll simply wrap this lovely floating point number in a string function, str. This will basically convert the floating point number into a string. And if we're already here, we might as well do it for B as well as for A because it's very, very similar. Cool, we can save this file. Now, another thing we just noticed is that we're not really getting 5 back. Even if we convert it into a string, we are getting 5.0 back. So what we'll do is we will slightly modify our test. Okay, even though I told you to modify the app itself, we're going to cheat a little bit here. So let's save it, and hopefully we are passing this test, because if it's not it, I have no idea how to fix it. Okay, so fingers crossed. There you go. Beautiful. We have successfully passed our test. Good job. This one was a hard one. So let's say that on top of input AB, we have also tested input BC and input CA. And to all my Canadian, Albertan, and British Columbian friends, no pun intended, okay? It's all in your head. In all cases, we have provided our app with 2 input values, and then we receive a single output value in return, which is ideal. But what happens if we're not dealing with the ideal scenario? What happens if the user, by accident, provided all 3 inputs instead of just 2? Let's check what happens. For this, we will go ahead and design a new test. We will copy our input AB1. We will paste it below, and we will modify it to input ABC, which kind of hints that it's a bit problematic because we're only expecting 2 of them, not 3. To test it, we will copy input B, and we will modify it to input C, focusing on the text input at index 0 rather than 2. Now we will do the same for the text attribute, copying input B, adjusting B to C, and then 4 to a string of 5. Great. Now before we assert anything, let's just check that there's some kind of output associated with the scenario. Okay, we're not sure what to assert yet. Let's go ahead and rerun our code. Ha! And there you go. Our app actually deals with this type of scenario. It has a special error message. If you already know all sides, then you don't need me. Perfectly logical. Now that we know that there's something to handle this scenario, we will navigate to my app. We will then find the scenario where all inputs have values that are different from an empty string, and then we will copy our return statement and paste it inside our test file. Now, we will, of course, get rid of this print statement. We don't need it anymore. And we will uncomment our assertion, passing the dictionary we just copied as a second argument of assert equal. Okay, save it, run our code, and yay, we now have successfully passed 7 tests. Great. So we've seen examples of ideal and accidental input. But how about testing the extreme ends of our input values, also known as boundaries? So for example, instead of testing for values of 5, why don't we test for values of 5 billion or gazillion or gugazillion or whatever large number you can think of? Now, on the other hand, how about instead of testing for values of 4, we will test for values of 0.000004. So we are basically looking for values that probably no one in their right mind will ever enter into our app, but because they are still considered as valid input, we absolutely have to test them. Next, what do we mean when we say mathematically wrong input? Well, how about dividing by 0? Or maybe specifying a negative side length, where length is a measurement that can only be positive. We will never have a length of -4, just as much as we will never be allowed to divide by 0. So here, we try to reproduce these bad math conditions and see if our software is able to properly handle them, where properly handling them doesn't mean collapsing and going on fire. We need a better solution. So let's quickly see a super quick example because this is not complicated. We'll just copy our test input AB and we will pass a negative side value to it. It's a good way of testing bad math. Okay, we will call this test input AB wrong. And then instead of setting the value of input B to 4, we will set it to -4, okay? And if that's the case, we definitely do not expect to get the original output in return, okay? So we will change this assertion to assert not equal. Let's save our file. Let's rerun our tests. And holy smokes, you guys, we found another problem with our code. It seems that our Pythagorean method has no issues with calculating a negative side length, which, may not collapse our app, but this is still wrong. If users provide us with a negative length value, we should not perform the calculation at all. We should stop and ask for better input instead. Now, because this video is so long, I trust you to fix it on your end. Please do. I know you can do it, but I'm going to skip to the last checklist item, which is actually my personal favorite, and it's called malicious input. Now, we generally assume that whoever is using our software has good intentions. We also assume that they interact with our software using traditional means. A good example of traditional means is running our software straight from the terminal with Python myapp.py, and that way, if we try to enter an input that is not a number, for example, G, K, L, T, H, it doesn't matter how many keys we press, I welcome you to try it on your end, our input will not be received by Kivy unless it is a number. So 5 is okay, 0.5 is okay, or any character that is associated with numbers. So realistically, if we try to enter the input of banana, the traditional, official interface will prevent us from doing so. But it doesn't mean that we cannot do it at all. In fact, our unit tests are a perfect example of interacting with software in non-traditional means. So here, banana is not going to work. But then if we go to our unit tests, okay, and if we comment out this failing test so it doesn't confuse us, then back in input AB, we replace 4 with banana. Do you think it's going to work? Let's see. Let's test it. Okay, we will run our tests. We will run our tests, not the app. And there you go. It looks like the Pythagorean method did receive an input of banana, even though Kivy was supposed to prevent it from happening. Okay, so this is clearly wrong, but why is it malicious? Well, the general idea is whenever our software enters this state of confusion, then bad actors can exploit it. So when our software is not sure what to do, it is vulnerable. That's why those malice checks are very, very important. We want to try to break our software from every possible direction. We can call it our form of pen testing in order to prevent other people from doing so in the future. Now, this banana example may not be devastating, okay? This will not generate a very malicious cyber attack, okay? But I'll give you the perfect example of malicious input. We call it SQL injection. Now, whenever we are dealing with databases and we allow users to search for terms within this database, there are certain inputs that will trigger an attack called SQL injection. This is full-blown hacking, guys, but it's so easy to do, it's just scary. I know it because I succeeded in doing so. I didn't believe it's going to work, and as a result, yours truly here is not allowed to search anything in Weather Canada. Okay, so if you're interested in SQL injection, please let me know in the comments below. I will dedicate an entire video for it. There's a lot of things to say. There's a lot of things to demonstrate. And I don't want you to try it on your end because you'll be blacklisted just as much as I was. And thank you so much for watching. If you found this video helpful, please share it with the world. And don't forget to leave it a huge thumbs up. If you have any questions, please leave me a comment. And if you'd like to be extra awesome, you can always subscribe to my channel, turn on the notification bell, and do all those things I usually say at the end of the video. And yeah, have yourself a fantastic day, and I will see you soon. Bye-bye.